Alright, so here we are with the objectives today for our 7-2 notes in Algebra 2, theoretical and experimental probability. So we're going to find the theoretical probability of an event and then also find the experimental probability. So, first thing we want to know about is probability. So it's the measure of how likely an event is to occur. Usually we think of probabilities in percentages, but you can also think of them as decimals from 0 to 1, or of course percents from 0 to 100. Sometimes we'll also talk about them as fractions, so 1 out of every 10, or whatever that happens to measure. So, we also have the word outcomes, and outcomes are the possible result of a probability experiment or situation. So the outcomes are the thing that you want or don't want to occur when you're thinking of a probability. The sample space is the set of all possible outcomes, and that's actually what we did when we were doing 7.1. We were finding that sample space. And then the event is an outcome or a set of outcomes. So this trial, for instance, or this round, we resulted in whatever it was. So, thinking of experimental or situation, we've got rolling a number cube. We do tend to call them number cube instead of dice. Either way, a number cube looks like it has 6 sides, so 1 through 6 is your sample space, meaning what are the likely outcomes. And then the spinner, for instance, you've got 4 options, and they list them there. So, sample space, it can potentially be listing them, or it could be that number of them, because I wouldn't want to list like the 200 options it could be. So it could be a total or an actual list. The next thing here is favorable outcomes. So favorable outcomes is the one that you are ending up solving for. So when it's 40% likely, it's 40% towards whatever the favorable outcome is that you have mentioned. It won't necessarily always be a positive experience, but it's the favorable one. It's the one that's being investigated. Then we have theoretical probability, and that is the ratio of the number of favorable outcomes to the total number of outcomes. So again, ratio meaning fraction. And so on top we have the favorable outcomes, so there they are, and then we have the total number of outcomes, and again that was from 7.1. And so we do often write our probabilities in this way here, P for probability, and then inside these parentheses we talk about what we want as our favorable outcome inside. So for instance, we might do probability of a king of hearts if we're doing a deck of cards, for instance. So sometimes we'll write the whole thing, sometimes we'll put symbols in, but the idea is that you're finding the probability of what's inside the parentheses. So we're going to find a theoretical probabilities. So here we are. Each letter of the word probable is written on a separate card, and the cards are placed face down and mixed up. What is the probability that a randomly selected card has a constant? So again, we're looking for the probability of a constant. Remember that the opposite of a constant is a vowel. So if we look at what we have in the word probable, we have 1, 2, 3, 4, 5, 6, 7, 8 total options. And then when we're talking about a consonant, those are the non-vowels. So we have 1, 2, 3, 4, 5 non-vowels. So it's going to be 5 out of 8. And again, a lot of us end up thinking about probability easier as percentages. So we would just take 5 divided by 8. And so we could say 62.5%. All right. The next one here is that 2 number cubes are rolled. This right here is the sample space, or the likely outcomes that could happen. And so the idea here is that we're imagining the first roll to be this red dice. So for instance, if I'm looking at this means my first roll is a 3, and then my second roll is this blue one, and it's a 3 as well. If I look at this one, for instance, it's saying the first roll is a 4, second roll was a 6. So that's how we use that chart. So 2 number cubes are rolled, and we want to know what is the probability that the difference between the two, so the subtraction between them, is 4. Alright, so there are a total of 36 cubes, and again we're doing the probability that the difference is 4. And so there are 36 because there are 6 options in rows and then 6 columns as well. So there are 36 options, and we want the value between the two numbers to be 4. So we definitely want 6 and 2. So let's see, there's that one and this one. 5 and 1 is also a difference of 4. Where's the other 5 and 1? There it is. And then I don't think there's anything else, because then this diagonal is a difference of 3, this is a difference of 2, so we don't have any more of those. Alright, so that means that there are 4 out of 36, and of course if you can, you would reduce, so that's going to be 1/9, but of course if you can, you also would put it as a percent, because it's a lot more digestible, so 11.1%. Alright, the next one is going to be the difference is 6, so probability that the difference is 6. And since 6 is the highest one, that would mean that we'd need a 0, but 0 is not on the die, and so that means there's literally 0 out of 36 outcomes, or 0%, or completely not possible. And then the red cube is greater. So the red cube is greater, meaning the bottom part here, because 6 is greater than 1. It's not greater than 6, but then in fact all of these are going to be where red is greater than blue. And so we're going to have less than half, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Hey, 15 out of 36. And of course you can reduce that as a fraction because they're both divisible by 3. So we'll end up with, we can have 5 12s, or we can have 41. I'm supposed to write point. 41.7%. It's a little sloppy, sorry. Alright. So, then we have something called a complement, and the complement is basically, well, here's our definition, the set of all outcomes in the sample space that are not in the favored event. So, for instance, the complement of winning would be losing. Okay. So, in this case, it's usually used with the word not, and so in this case, the probability of the complement of event E is, well, that not E is occurring. And so a lot of times this is used, especially when there's a very large list. So, for instance, it would be hard to say, I want to find the probability that I'm going to draw a M out of a bag of letters of the alphabet. But if I wanted to find the opposite of that, it would be a lot easier to just say the probability of not M versus the probability of listing everything other than M. So it's usually to save time. It's also to save time when it comes to actually calculating it, because then you can actually do 1 minus the probability that's actually easier to find, the probability of M, versus counting out the probability of all the other pieces. So, that might have been helpful, I mean not really, but in this other one, where maybe we would say, what is the probability that it is not a difference of 4? And so that would mean that we would do 1 minus that 1/9, and so we'd get 8/9. Whatever. Anyway, that's the idea. So, here we have an application. There are 25 students in a study hall, and the table shows the number of students who are studying in a foreign language. Excellent. Studying not in a. What is the probability that the randomly selected student is not studying a foreign language? So, not studying a foreign language would be a 1 minus the probability that they are studying. So what we have here is the fact that there are 25 students total, but in this grouping there are 21 students listed. And so we are going to do 1 minus the probability that we do know that they are studying a language, which would be 21 over 25. And so that means that we're actually going to get 4 out of 25. as not studying. And of course you can put that in its percent form if you would like, which just means that you take 4 divided by 25, which is 0.16, but that is, of course, 16% if you move the decimal twice, or multiply by 100. So, this here, two integers from 1 to 10 are randomly selected, and the same number may be chosen twice. So what is the probability that both numbers are less than 9? What happens when we end up seeing this less than 9 idea is that, as we were talking about with the complement earlier, it's easier to actually do 1 minus the probability that the number is, the number is greater than or equal to 9. Because we do have less than 9, and so that's actually quite a few of them, and so it's easier if we just do 1 minus the probability that it is greater than, the number that we've gotten is greater than or equal to 9. So that's the same as less than 9. So, how do we do that? Well, let's see. We're going to do 1 minus the probability that a number is greater than or equal to 9. So, looking at the list from 1 through 10, the only ones that are in that list are 9 and 10 that are actually greater than or equal to 9. And so that means that there are 2 out of 10 options, and so officially that's 8 out of 10. And again, these are all theoretical probabilities, because we didn't actually draw the cards themselves. Alright, then we have something called geometric probability, which we actually end up skipping in the actual geometry class. And that's because the idea is pretty simple. It's like a dartboard, for instance. And so you're saying, I'm going to throw a dart at this, kind of target idea, and what is the probability that I would get in this circle? Well, it would be nice if we then knew what the volume of, area of this circle was in comparison with the entire area, because then we can say, okay, well, it's the shaded area over that non-shaded area. So it's going to be very direct on what it is that you end up finding. So right here, for instance, we have our geometric probability. They're saying, hey, guess what? There's a circle and a square and a rectangle and a triangle. And hopefully we know our basics of that. A square or a rectangle is going to be an area of length times width. And then a triangle is going to be an area of a half of base times height. Alright, so taking a look at this, again, a figure is created by placing a rectangle inside of a triangle, inside of a square, if a point inside the figure is chosen at random, so we kind of throw a dart, if you will. How likely is it that the point is inside the shaded region? So how likely is it that it would make it into this area? Now, of course, there's the option that it could just be like not in any of the areas, but that's not really the point of what we're doing here. So, what is the likelihood that we're landing inside here? Well, we're going to need the entire area of the whole thing, and the whole shape is going to be a length times width, so we're going to have length times width, which is actually 9 times 9, because our width here is 9 centimeters. So we know that our entire width, or our whole shape, has 81 centimeters squared inside of it. But then the part that we're actually looking for, that shaded region, is going to come from taking that area of the triangle and subtracting out the area of the rectangle. So the area of the triangle is a half, and then the base is 9, and the height is 9. And to that, we're going to subtract the rectangle, which is length times width, so 4 times 3. So that's going to result in 40.5, because 81 divided by 2 is 40.5, minus 12. And so the area of the shaded region is going to be 28.5. Officially, that means that we are finding the probability of being in the shaded region, and it's going to be 28.5 over 81. Or if we divide those, we end up with 35.2% likely. So that's a little bit more than a third of the entire region. Alright, now instead of theoretical probability, we're going to talk about actual experimental probability. So for instance, actually throwing a dart at this board and seeing if you get in the shaded region versus not. So an experiment is used to estimate the probability of an event by using collected data. This is actually kind of the basis of most science, well, of all science, which is doing those experiments enough to say that, well, in theory, we are going to assume that it continues this way and it will be that way. So, for example, if a doctor states that an operation has 80% probability of success, 80% is an estimate of probabilities based on similar case history. So similar people with whatever it is that you have that you're getting an operation on, or whatever it happens to be, based on your height and weight and who you are, that kind of thing, on how successful it will be. A trial, then, is each repetition of an event. So most of the time we think of rolling a dice or flipping a coin, but a trial is each of those. Therefore, the experimental probability is the ratio of the number of times that the event occurs, so that you flip a heads or that you flip a tails, and then the frequency to the number of trials. So the heads over, I flipped it 10 times. Alright, so here we are with the experimental probability. How you formulate it is a fraction, just like theoretical probability. And so we just, again, look for the number of times the event occurs over the number of trials that you actually do it. So you don't need that counting principle. You just need to say, well, how many times did you actually do the experiment? Experimental probability is often used to estimate theoretical probability and to make predictions. This is kind of what I was talking about earlier with scientific theory. And how if you do things enough times, have as many trials as possible, you can reasonably assume what the outcome will be. So here we are with finding the experimental probability. It's our last example. The table shows the results of a spinner experiment. We need to find the experimental probability of spinning a 4. And so this is, again, based on whoever it is that's happened to be spinning the spinner, right? Someone's going to maybe put more force into it than another person. So this person, when they are doing it, the number of times that they spun the spinner would be adding these all together. So your total is going to be that all together, which is 30, 40, 50. And then they want you to identify a 4 happening. And so that means that we are going to talk about the number of times that we want it to occur over the number of times that actually happened. So 14 times within 50 spins. Of course, that can be reduced because they're both even numbers. And so we can get 7/25, or of course we can get the percent, which would be 28% of the time. So just so we're aware, there are a lot of keywords in theoretical and experimental probability. So of course there's probability, the likelihood of something occurring. Hopefully you also know sample space. Again, that's usually the denominator when it comes to theoretical probability. Favorable outcomes, that's usually the numerator in a theoretical probability. Theoretical is different than experimental probability because theoretical is what we expect to occur, but of course experimental is actually what occurs. Geometric probability is the one where we're talking about the shapes. Usually there's some sort of shaded region going to be divided by the total area. Trials are what we're talking about when we do a series of experiments. So each of the times that it's done is your trial. Outcomes are your results. Events are made up of trials. Your complement is the one that is opposite. So again, remember that usually means not, or 1 minus some sort of number system. And then, of course, your experiment is the whole setup of what it is that you want to find the probability of, what event you want to occur or not to occur. So those are your vocabulary for 7-2. And so hopefully we know a little bit about the difference between theoretical probability and experimental probability, and then all of their little subsystems.